Hi everyone, in this video we'll start with galaxies and end with cosmology. The picture on the slide right now is William Herschel's conception of the galaxy. William Herschel was an English astronomer, and he came up with this picture simply by looking at the sky and measuring stars and counting them and figuring out how many he could see. He assumed that all of them had the same brightness. So if he saw more stars, then he figured that there was a longer extent of the galaxy in that direction. So he's here at the sun, and he looks in this direction and sees lots and lots of stars and infers from that a finger of the galaxy that stretches farther away from him in that direction. He came up with this kind of oblong disc-like shape, sort of, and today we conceptualize galaxies such as our own Milky Way as a disk that looks a little bit more like this. This isn't the Milky Way, this is actually the Andromeda, our sister galaxy, but it has a lot of the same structure that we think the Milky Way has. So here is the galactic bulge in the center of the galaxy, and here is the disk, the galactic disk, and a halo that you can't really see, but that is in 3 dimensions around the whole galaxy, sort of surrounding it. And those are kind of the 3 big parts of our galaxy. The disk is blue, and the reason it's blue is because there's a lot of matter there, and that matter is actively forming stars, including some very bright, very hot stars. It's forming stars of all sizes, but of course we see the brighter ones more clearly because they're, well, brighter. So this disk we'll put as blue because blue is the color of the hottest stars. And those hot stars tend to burn out their fuel quickly. So they're not around for very long, but then more of them form because the matter is so dense in the galactic disk. So we still continue to see it as blue. In the bulge of the galaxy, it's yellowish, and this is because in above and below the galactic plane, the matter is less dense. And so because of that, there's less star formation, and so more of the young hot stars have burned themselves out, and you see more of the reddish stars. So the bulge is yellowish. And then the halo, as you might imagine, we're going from blue to red. In the halo, there are only older stars that are redder because the young ones have burned themselves out already. And we can understand how this has happened by thinking about the formation of the galaxy. So it formed in much the same way that our solar system formed. When it started to develop, the matter started clumping together, and the disk initially had some non-zero rotation, just only because it's extremely unlikely for that rotation to initially be exactly 0. So stars that formed in the halo didn't really have a preferred rotation direction. They weren't in the disk. And they're still there. They're still in the halo, but the ones that were there in the beginning are gone because the hot ones, rather, that were there in the beginning are gone because they've burned themselves out. And as time passed, matter from the halo began to fall in toward the galactic disk because of its gravitational attraction to all of the stuff that was in the disk. And that's still happening today. The matter continues to fall inward, and it's been measured toward the galactic disk. So there's less matter available for star formation in the halo now than there was when the galaxy was forming. And that's why there are only old stars in the halo, not any of the young new stars. And all of the ones that were bright and blue, the hot ones, have all burned themselves out because they go through their fuel more quickly, just like a very large minivan will go through fuel a lot more quickly than a small, sleek car will. In the innermost part of the galaxy, the density is extremely high, about 100 million times greater than the density of stars in our solar system's neighborhood. So if we could see past the dust that obscures our view of the innermost part of our galaxy, we would probably be seeing collisions of stars much, much closer together than they are here, and certainly quite a lot of active star formation in that very dense area. So you can see why the disk is blue. This is where the young stars are and the forming stars are and the hot stars are. And then where matter is less dense, above and below the bulge, and then also in this three-dimensional red halo, the stars tend to be older and redder because the blue ones are gone. In the Milky Way, we can learn a little bit about how things are rotating by looking at Doppler shifts. So here's the sun. We're rotating around the center of the galaxy at about 240 kilometers per second. Here's the rest of the galaxy, the spiral arms of the Milky Way galaxy sort of stretching out. And because of differential rotation, meaning that things that are closer in go faster. That law that we studied way back at the beginning, closer, faster, farther, slower. So something down here below us, closer to the galactic center, is going around much, much faster than the sun is. It's leaving the sun behind in its rotation. So imagine if you're a star, imagine if you're a star right here, you're going much faster than the sun and you're leaving the sun behind. So therefore, viewed from the sun, something down here is getting farther away. Something kind of in this quadrant is getting farther away. It's receding from us. Whereas if there's a star up here where I'm now pointing my arrow, we're catching up to it because it's farther away. So it's still rotating, but it's rotating more slowly than the sun is. And therefore, we're catching up. So if it's receding from us, it will be red shifted. If we're catching up to it, it will be blue shifted. And so we can do this for the other quadrants too. So down here, this star is rotating faster than we are. So it's catching up to us, meaning it's getting closer to us, meaning its light will be blue shifted. Up here, a star that's right up here is going much more slowly than we are, meaning that we are receding away from it, we're leaving it in the dust, and therefore it will be red shifted. So we can draw this kind of diagram with the sun right here and understanding which stars will be blue shifted and which stars will be red shifted based on their position relative to us and relative to the center of the galaxy. And blue shifts and red shifts are going to be what we use to understand some other ideas in cosmology too. But to get there, we first need to talk a little bit about distances. This is the distance ladder. And I said at the beginning, if you want to get two astronomers into a fight, ask them about distances to things because there are lots of approximations and many different ways of doing this. But this is kind of a big picture summary of what's going on. Radar ranging we can use for close objects within our own solar system. We shine a light at something and wait for it to get reflected back and measure how long it took and calculate the distance. And that works great for things that are close. But then if you start getting farther away, your electromagnetic signals become weaker, inverse square law, and also it takes longer for something to get back. If we wanted to try that with something several light years away, it would take several years to return the signal to us. So we also use stellar parallax, and we said that that can get us up to 200 parsecs using the Hipparcos Space Telescope, which is pretty awesome. So, that's a long way away to use parallax for. However, our galaxy is 33,000 parsecs roughly in extent, so it doesn't even really get us out of our galaxy to use stellar parallax. We can get farther by using spectroscopic parallax, which we talked about before. Remember on this HR diagram, the vertical axis is luminosity. And if we know how bright something really is, so its luminosity is how bright it really is, and we can also measure how bright it appears to be just by how many photons hit our telescopes, then we can make an inference about how far away it is because we know the inverse square law of the distance. So just like you did for the sun, the light bulb lab, with the measuring the distance to the sun based on that oil spot photometry experiment. So all of the techniques from that up use this principle. We figure out how bright something really is, we measure how bright it appears to be, and then we use that to infer the distance to the thing. And so variable stars are another way of doing that. It happens that stars flicker when they end their lives at a particular point on this HR diagram. So they start leaving the HR diagram to become red giants, and for a few million years there's a period of instability where they flicker. And so we can measure the extent to which they flicker. In this case, the y-axis is the luminosity. We measure the period of their flickering, and that tells us where they are on the HR diagram. And as soon as we know that, we're golden because we know their luminosity, and then we can measure their brightness and figure out how far away they are. That gets us farther than spectroscopic parallax. And then for entire galaxies, which are very far away, we can use this Tully-Fisher relationship, which depends on how fast they're spinning. How fast they're spinning can let us know how massive they are. And then, as we saw many times before when we were doing dark matter, so we can calculate the mass of the galaxy by how fast it's rotating. And then once we have that, we can make an inference from its mass about how luminous it is. And then once we know how luminous it is, we can measure how bright it appears to be and get the distance that way. And finally, this last technique is standard candles. So these are things that have a known luminosity. Type 1 supernova are a great example. Stars explode in a type 1 supernova when they get to a certain mass, and the explosion has a brightness, a luminosity rather. Luminosity is how bright it really is. The explosion has a luminosity that is standard, so we know how bright it really is. As soon as we see the signature of one of these type 1 supernovas, we can measure how bright it appears to be and compare it to how bright it really is and get the distance that way. And that can get us big distances, like 200 megaparsecs, where mega is million. All the way up to a gigaparsec, which has a lot of zeros on it. So that can get us to very, very far distances away. And of course, when we're that far away, we're looking back in time, because the light that reaches us is light that had its origin that many years ago. So these distances can be vast using these techniques, but again, there's a lot of fights among astronomers about how they should be used and specific ways in which to use them. So we use them. Let's just say we're using them. And then we're looking at Doppler shifts of galaxies and also of clusters of galaxies, because there's larger scale structure in the universe than just galaxies. So, and we find this, we get blue shifts from Andromeda and a few other galaxies that are close to us in our local group. They're moving toward us. But other galaxies that we measure and galaxy clusters are moving away from us. And the farther away from us they are, the faster they're moving away from us, which is weird because it seems counterintuitive to think about that. But look at this graph. The distance is millions of parsecs on the horizontal axis. And on the vertical axis, we have the recession velocity, which is the speed at which the galaxy or galaxy cluster is receding. And you'll notice that the closer a galaxy is, where, you know, it's kind of funny to say close and mean something that's millions of parsecs away, but as galaxies are closer to us, their recessional velocity is smaller. So that means that they're not moving away from us as fast. And indeed, Andromeda, as we said, is actually moving toward us, but that's from kind of a different effect that we'll talk about in a second. So what we infer from this is the recessional velocity's relationship to the distance. It fits this line really, really well. And this Hubble constant, h0, is the slope of the line. Just like you would make a slope for a line, rise over run, right? Recessional velocity in kilometers per second divided by distance in parsecs. And the slope of that line has been measured, and it's being measured more and more accurately by more and more astronomers, and its current value is 70 kilometers per second per megaparsec, because recessional velocity is in kilometers per second and distance is in millions of parsecs, megaparsecs. And we infer that for Andromeda and these other galaxies that are close to us, local gravity is winning because gravity is an inverse square law, and the stuff that's close to us, that r squared in the denominator, is small enough that we have a large enough gravitational attraction to Andromeda. The Milky Way as a whole has a large enough gravitational attraction to Andromeda that they're going to eventually collide, and they're moving toward each other. They're attracted to each other gravitationally. For things that are farther away, though, space seems to be expanding. They're getting farther away as they get. They're moving away faster as they get farther away. So at large distances, we say at cosmological distances, we get this increasing recessional velocity with distance. This is called the cosmological redshift, because as things are moving away from us, their spectra are redshifted farther and farther, more and more deeply, the farther away they are. So there we have it. We started at galaxies and we got to cosmology. Thanks for watching.